Welcome back. So this is the theorem. I think we had it on the board, so I took the liberty to write it on the board again. Right. We are talking about topological dynamics, so we, most of the time, usually will have a compact metric space, X, and we'll have a homeomorphism. Some examples are not invertible. Some of the theorems could be phrased more generally, non-invertibly. Never mind that. Most of the time, I just want to assume my map is a homeomorphism from X to X. Then the following are equivalent. T is minimal. Minimal means that every orbit is dense. If I have a closed T invariant set in that strong sense, that E is equal to TE, then that closed invariant closed set is either nothing or the whole thing. It's an equivalent condition. Or if you have a non-empty open set and you take the orbits kind of the non-empty open set and take the union over the orbit, you actually get the whole space. Which of course also means that only finitely many are sufficient to do the same thing because it's an open cover of a compact space. Right, and we want to prove that. We already talked a little bit about it. The proofs are rather straightforward, just like the things that we did last week. They were so far still very straightforward. 1 implies 2. Suppose E is equal to TE is closed and non-empty, so there exists a point inside. But if I have a point inside and I'm assuming T is minimal, then every orbit is dense, so in particular the orbit of this X is dense, then O of X closure is equal to X, but O of X is contained in E because T is an homeomorphism invertible, so I didn't write it down, but E is also T inverse of E. If I apply to this equation T inverse, which I may, I get E is equal to TE is equal to T inverse E. So the orbit, both-sided, is actually inside E. And if I take the closure, I see that the space, the set E is everything. Because E is closed and the orbit is dense, so there's no way around it. 2 implies 3. Let U be open. Then U twiggle, which is this union over all n in Z of TNU, is open, and T of U twiggle is U twiggle. Hence, when I take the complement, E is equal to X without U twiggle is closed, and TE is equal to E. T is bijective, so it works very well with taking complements. So 2 tells me that E must be nothing or everything. So by 2, E is nothing or E is everything. If U is non-empty, then U twiggle is non-empty. So then E equal X is impossible, so E must be not the empty set, and 3 follows. As I said, quite straightforward. Last one, 3 goes to 1. Let X be in X, some given point. We want to show its orbit is dense. Let U be non-empty and open, so that the union over n in z, t to the nu, is equal to x by 2, 3. Right, if I take the non-empty open set, take the orbit and the union, I get the whole space. That's my condition in property 3, which means that this union must contain our x0. Hence, there exists some n, an integer with x0 in t to the n u. But that's equivalent to t to the minus n being in u. Or equivalently, t to the minus n x0 belongs to u. So what did we find? We found a point in the orbit visiting this open set. The open set was arbitrary, and the orbit hence needs to visit all open sets, so the orbit must be dense. This shows that orbit of x0 intersected u is non-empty for any open non-empty u. Hence, O of x0 closure is equal to x, and 1 follows, because I had no condition whatsoever on x0. Do you have questions? About this, about what we did last week? No, good. Then, it's a nice proposition, it's a nice property, but will it ever exist? Do minimal systems exist? And there's a nice theorem that says quite generally that minimal systems exist. Of course, it can't say that every system is minimal. It's easy enough to find systems that are not minimal. But every system that you can think of will contain a minimal subsystem. And that's the theorem. Theorem, let X be compact metric and T from X to X be a homeomorphism. Then there exists a closed, non-empty Y contained in X with, so that Y is equal to Ty. Every point is orbit, has an orbit and pre-image within Y. Future point and past points in Y. And T restricted to Y from Y to Y is minimal. Let's postpone the proof for a moment and just obtain an immediate corollary, which isn't so easy to get without that theorem. Corollary. Let T from X to X be as above. Then there exists exist points, at least one, x0 in x, exists, I should say exists a point. I don't know whether there are many. There exists a point x0 in x, so that t to the nk x0 converges to x0 as k goes to infinity for some nk going to infinity. Said differently, there exists a point that belongs to its own omega limit. There exists a point that will come back to its neighborhood again and again in the future. Maybe in the far future, but it will again and again visit its own neighborhood. And that's true for any neighborhood, so we can find a subsequence that actually in the forward orbit that converges to our point. Such a point is called a recurrent point. So let me give you this name. Definition, x0 in x is called recurrent for t from x to x if x0 belongs to the omega limit under the map of x0. Okay. I'm claiming the corollary is very easy. So let's do the corollary first. Proof of corollary. Let y in x be as in the theorem. Let x0 in x in y be arbitrary. Because actually we'll show in the corollary that in a minimal system every point is recurrent. And the theorem just says a minimal subsystem exists, and then within that subsystem every point will be recurrent. Then omega plus of x0 will be inside of y, right? And I'll leave that as an exercise. Omega plus of x0 is a t-invariant closed set. And omega plus x0 is a t-invariant closed set. Exercise. I'll actually generalize this exercise a little bit later, and then I think we'll put it into the exercise sheet for next week so that you have time to talk about that step. It's a t-invariant closed set. By minimality, omega plus of x0 equals the empty set or equals the minimal subsystem y. Right? There are only these two possibilities because y was minimal. Right? Y is invariant. What do I mean by invariant? T y equals y, right? As in the theorem. So the orbit will definitely be in y, and the orbit is closed, that's the exercise, and invariant. So minimality of the subset y kicks in and tells you that the omega limit must be nothing or everything. It can't be nothing because we're working inside a compact space, and the omega limit is defined as all possible limits of subsequences. There exists a limit of a subsequence by compactness, so this is not happening. by compactness of y in x. We also know omega plus of x0 is not the empty set, hence omega plus of x0 is the minimal system, and the minimal system contains the initial point, so the initial point is recurrent. Let me just state the exercise in the generality that I want, so that we are done with it. Exercise. Let X be compact and T from X to X a homomorphism. Let, what letter do I want? Just E, some subset E in X be non-empty, a subset. If it's empty, it's easy, not particularly interesting. Then I define the omega limit of the set under the transformation T as all possible limits as k goes to infinity of T to the nk of xk, where xk is an arbitrary sequence from the set E, and nk is a sequence that needs to go to infinity, so that it kind of has really looks at the omega limit for the future, kind of. And the exercise is saying, prove that, and that's true, T is equal to omega T plus of E. E is the omega T of that is equal to the omega limit of the set, and it's also closed. So what I'm saying here is more generally true even for a subset, but it's also true. And it would also be true without assuming homomorphism. It would also be true if it's just a continuous map. I'm not fixing it. Maybe it's appearing in the more general version in the exercise sheet. We'll see. Okay? I don't think the proof is very hard. You just have to sit down and think what you need to prove when you show that something is closed. You have some practice in that, so practice it a bit more. It's not bad. Okay, the theorem I keep there. The rest I erase. The theorem we don't know yet, right? It's kind of nice because it's concise, right? It doesn't have so many assumptions, and even so, it has a useful conclusion. So it's nice. But somehow maybe that hints at that it can't be super constructive, because it's so general. How can something like that be stated and proved so generally if it would be also kind of constructive? That seems unreasonable to hope for. So presumably this will use the axiom of choice in some way, so we use the lemma of Zorn. Why not? Proof using Zorn's lemma. We define the collection of sets. Doesn't matter, give it some name. We look at all y's that are contained in X. Y should not be empty. We don't like the empty set. Y should be closed. And Y should be invariant in the strongest form. T of Y is equal to Y. Okay? So obviously it's non-empty because it contains the whole space. The whole space is closed, it's non-empty, and is invariant. So it's a non-empty collection of sets. In Zorn's lemma, one usually tries to find an upper bound somehow, a maximal element from the set, something like that. But of course, we are interested in a minimal set, so we use the reversed order kind of thing. I'll not make a big deal out of it. We define the collection and wish to use Zorn's lemma for inclusion to find a minimal element in E. There's only one thing. Yeah, okay. There are some things to check if you want to use Zorn's lemma. You want to have a partial order. Check. But the main thing, the most important thing to check is that if you have a chain of things, a chain of elements in E, not necessarily a countable chain, and we are thinking sort of a decreasing chain. If you have a chain of elements in E, and by chain I mean that it's a linearly ordered subset, then you can find from within E another element that's smaller than all elements in the chain. And it couldn't be easier than in this example, because if you have a chain of things, just take the intersection and show that it satisfies everything. And it will satisfy everything. And only once maybe you have to think a bit, but even that is kind of obvious. Namely, if you have an arbitrary intersection of closed sets, this arbitrary intersection of closed sets will be non-empty if any finite subcollection of sets from the set, or from the family of sets, will have non-empty intersection. But if it's a chain, finally many have a minimal element, and then the intersection will be the minimal element. So that intersection will never be empty. A finite intersection from elements from the chain is never empty. And then compactness comes in and tells you that the whole intersection of all elements in the chain will be non-empty. That's the only thing that requires a bit of thought, and where we'll use compactness and the set that our sets are closed, and everything else will be automatic somehow. So let me write down a bit to prove to be able to use Zorn, we have to show that for any chain in E, there exists a lower bound in E. And I already said everything that needs to be said, but I'll write it down so that we have it on record. Let Y alpha in an index set, be a linearly ordered chain in E. So each one of them is a non-empty closed invariant subset of X, right? We define Y to be the intersection over all sets in the chain. Clearly, ty equals y is closed. To see that y is not empty, we apply chain and compactness. For alpha 1 up to alpha n finitely many indices, we have that the intersection of y alpha 1, y alpha n is equal to y alpha j for some j from 1 to n, because we have a chain, a linearly ordered chain. We have a linearly ordered chain. Hence, this intersection is non-empty. Compactness of x now implies that y is non-empty. Everyone is happy with that argument? So Zorn's lemma implies that E contains a minimal element let's call it maybe, yeah, let's call it y. Then t restricted to y from y to y is minimal because it cannot contain a proper non-empty closed subset. See proposition from earlier. Right, in the proposition before we said a system is minimal, meaning every orbit is dense, if and only if it doesn't have closed invariant subsets other than everything or the empty set. And our minimal subset will not have smaller closed subsets because it's a minimal subset, and hence the dynamics on that minimal subset will be a minimal dynamical system. Every orbit will be dense, every omega limit will be everything on that minimal subset system. So maybe it's time to see a minimal system. Because, yeah, sure, it's nice to have as an abstract theorem that minimal systems exist, but it's even nicer to have one and know one in person and not just, yeah. So I'm claiming the circle rotation for an irrational angle is minimal. And we want to show that. And many things will get much easier later in the course. Including this example will be we will know much more about it, and the proofs will actually be easier later on, even though we want to aim for stronger statements later on. But so is life. If you use the right tools and the right things, things might get easier, and they will get easier in 2 weeks' time or something. But yeah, it's still good to have an example, so let's discuss it. Let alpha be not in Q, and T, let's call it R alpha, the rotation map that maps X in the torus to x plus alpha in the torus. Then this rotation map R is minimal. And I want to prove that. I want to show that every orbit is dense. But I intentionally want to show it now and not earlier, because now I can use the corollary. The corollary says there exists a recurrent point, right? So let me do that. By the corollary, there exists x0 in the torus, so which is recurrent. Let epsilon be greater than 0, then there exists some n, some integer, representing a future point, so that the distance between r to the n x0 and x0 is less than epsilon. What is r to the n x0? That's x0 plus n times alpha and x0. That distance is less than epsilon. But we're on the circle. And we already defined the metric on the circle, just using the regular distance in the real to define the metric on the circle. If you translate on the circle, I said that before, metric is actually invariant. So you could translate by x0, and the metric is invariant. So actually, this is a statement about n alpha, namely that n alpha is epsilon close to 0, as the metric is translation invariant. We obtain the distance of n alpha to 0 in the torus is less than epsilon. But alpha is not a rational number, so n alpha can't be 0. It can be super close to 0, that's okay, but it can't be precisely 0. As alpha is not in Q, we also have n alpha is not equal to 0 in the torus. Not equal to 0 in the torus means that it's not an integer in the reals, right? Not being an integer in the reals means precisely alpha not being rational. Okay. So the x0, the recurrent point, is now gone, right? We don't have it anymore in the discussion. So now we can take another arbitrary point, x, now an arbitrary point. x0 was special, chosen from the corollary, chosen after Thorne's lemma and so on. x0 was very special somehow, potentially. But now we take an arbitrary point. Let x be in the torus. Yeah. Then x plus minus n alpha. I draw it. So here's my point x. And then I add and subtract the n alpha. So I get some other element that's epsilon close to x here somewhere. Maybe epsilon is like this, but I have a point that is rather close. And then I have x plus and x minus. I don't know which one is which. I don't care. So this is x plus minus n alpha, and the other one is x minus plus n alpha. And I do the same with x plus minus 2n alpha. I do the same with all the other guys. And I do the same with x plus minus. I take 1 over kind of the distance of n alpha to 0. Right, I said this n alpha is not 0, so the distance is positive, so I can divide by the distance of n alpha to 0, take the integer part of that, and use that as a coefficient in front of n alpha. So if you think about it for a while, you'll see that by taking really all these finitely many points going, say, to the right and to the left, so somewhere is maybe 0, maybe here is 0, maybe here was 1. I didn't hit that. And to the left, I do the same thing. I really see that the unit interval will be almost covered by my orbit up to a mistake of that is less than epsilon, because the gaps between those two is less than epsilon all the time. And all the points that I draw, all these points, they are contained in the orbit of x, and the finite list is epsilon dense in the torus. Is epsilon dense in the torus. But epsilon is arbitrary, x is arbitrary, so every orbit is dense. This shows that every orbit is dense. Yeah, maybe in the sense of analysis 1 exams, maybe this is not yet super formal, but there's only a bit of bookkeeping why this is the right number and so on. I think it's perfectly fine to leave it as it is. Unless you have questions about it, then we can talk about it. Let me give you one more notion, which is of slightly different nature, but it's sometimes a nice notion. And yeah, depending on how long that takes, we start another big topic, either just after the break or after this definition. Definition, let T from x to x be a homeomorphism. Once more, if it's not invertible, one could still define a notion similar to that one, not assuming invertibility. We say T is expansive not expansive, but expansive, sort of expanding things in some sense, if there exists a uniform delta called the expansive constant. The expansive constant delta greater than 0, so that for any 2 points x not equal to y in x, they will be delta phi apart at some point in time. There exists n in z, so that the distance between t to the nx and t to the ny is bigger than delta. So that's kind of saying the opposite of preserving the metric, kind of an opposite of preserving the metric, because if it's preserving the metric, then this would imply that the space is finite. Not compact, but compact would imply finite. So the rotation map is not expensive. If you take 2 points that are delta close together, distance less than delta, they will have less distance delta all the time, forward and backward, all the time, right? Because the metric is preserved. But here I want precisely the opposite. No matter how close together they are initially, at some point, possibly in the past, but at some point they have been delta far apart from each other. So if I say it differently, if I have a very poor eyesight and I want to know that 2 points are the same or 2 points are different, I'm able to do that if my system is expensive, even if my eyesight is poor, because I only have to watch it all the time, and if the points are different, I'll be able to say they are different because they will be doing different things at some point in time. Okay, so definitely we have an example that's not expensive, but we can also find examples that are expensive. So let me give you an example. It's this hyperbolic toral automorphism, for instance. TA x1, x2 in the two torus is mapped to x2, x1 plus x2 in the two torus defined by A, which is 0, 1, 1, 1, is expensive. It's actually many other things too, but they're maybe at that point a bit hard to prove. Again, things will become easier. It's actually topologically transitive and also topologically mixing. Not isometric. The metric is changing because, yeah, it's expensive. What else can I say about it? Not minimal, right? That I can also say. Not minimal, which is easy. Why is it not minimal? Yes?
0 is a constant.
Yeah, 0 is a fixed point. The whole space is much bigger, but 0 by itself is an invariant subset. Its orbit is just 0. So it's not minimal, definitely not. Topological transitive and mixing, maybe they are... I could draw a picture that sort of indicates why this should be true, and maybe I draw the picture. So I said before that there is this orthogonal basis into an expanding direction and a contracting direction at every point. And if you have an open set somewhere, it doesn't matter where, you could still think of these two directions. And let's say we go forward in time, then this little circle will become an ellipse. And it will get much bigger in the direction of the expanding eigenspace. But thinner in the other direction, which I didn't draw so well. And if you keep going and apply huge power, this in the direction of the expanding direction, it will be super long. And this super long line segment will start to wrap up and become dense in the torus, in the two-dimensional torus. But making this sort of precise then requires you to show that this direction is kind of irrational, and that an irrational line, if you draw it very long, will have to wrap around and become very dense in the space, which actually relates a bit to the example from before, in some sense. But we'll do it later. Later it will be much easier. And we can do other things more generally with the techniques from ergodic theory. So it can be done, but it will be easier later. Minimal is easy, as we said, because of the fixed point. And expensive is not too hard either. So that is something you could check. And you just sort of analyze the displacement, x and y, sort of 2 points. They differ by some vector in R2. And it's kind of unique because you just want a small displacement. If the 2 points are far apart, forget it. Then it's already done. You don't need to think about it, right? If they are distinguished at time 0, we forget it. So we think of 2 points that are very close together at time 0. So the displacement is a small vector. And then the mod C2, the integers are not so important because they would create bigger vectors. So you think of a small displacement and think of the decomposition into expanding and contracting eigendirection. And then you can show with linear algebra kind of that it's an expensive system. Yes? Thank you. N is in Z. That's why I assumed homeomorphism so that I can also look at the negative time. So if it's in the contracting space, forward time will not do anything, but backward time will at some point pick it up and expand it enough so that I can see it. Thank you. Let's do the break. Gibt es Fragen zu? None. Are there questions to what we discussed? No? Good. Then bring some questions next time. And now I want to convince you that dynamics, dynamical thinking, dynamical methods can be useful to other areas of mathematics as well. Not only do we need lots of technology from other courses, like, of course, topology, topological metric spaces, some compactness, Baire category. This is all sort of from topology. We use all of that. In 2 weeks, at latest, we'll start ergodic theory. And you could think of ergodic theory as the reason why you learned Lebesgue integration, because it will be very useful in dynamics. And to understand many examples, Fourier series harmonic analysis will be just super cool to have. So look forward to that in analysis 4 if you're having currently analysis 4, because again, you want to learn that so that you know our examples that we already saw and we'll keep seeing sort of, yeah. Harmonic analysis is cool for us. But as I said, dynamics can also be not only customer, it can also be service provider to other areas of mathematics. And I want to show you that by prove a theorem from combinatorics using topological dynamics. So I first give you the theorem from combinatorics. Then we'll talk about the topological counterpart and prove the topological counterpart. And maybe late tomorrow or next week, we'll then do the deduction how to prove the recurrence theorem and how the combinatorics theorem using the recurrence theorem that we'll start doing today. So what's the combinatorical theorem? It's a theorem of van der Waarden. And I'm hoping to get the spelling right. That's the most difficult thing about the theorem. No, the theorem is easy to remember. It's a cool theorem, but the spelling is harder. So let Z equals B1, disjoint union B2, disjoint union BK be a finite partition So how many do I have? Yeah, okay. I have 3 colors. So if you're a combinatorialist, you would think of a finite coloring of the integers, right? Then, that's the only assumption. Then there exists B equals Bj, so one of the sets. That contains arbitrarily long arithmetic progressions. So what do I mean by an arithmetic progression? A plus the difference, A plus twice the difference, and so on. A plus n times the difference. They are all in the same set for arbitrary n. N is the length of my progression, and sum a and d in the integers. So of course the beginning, the a is also from my set, but the difference, I don't know whether the difference is in my set b. I'm not saying that. But there exists an arbitrarily long monochromatic progression, arithmetic progression. It's monochromatic, it has only one color because it's in one and the same set of my partition of the integers. It's part of Ramsey theory, which you probably have heard of before. And the idea in Ramsey theory is that given a structure, a big structure like all the integers, it's kind of hard to completely destroy this structure. Because this long arithmetic progression, it looks like the integers. Of course, it's a finite piece of the integers, and you have to look at it from far away because you had many colors and the colors may alternate, so the difference might be large. But this kind of structure that you have, this monochromatic sequence of points that are at the same distance from each other, you cannot destroy. If you use 20 colors, it doesn't matter. You will be able to find this monochromatic finite progression. Longer and longer within one of the colors. Okay.
So does there exist an A and a D such that the whole progression, like the infinitely long progression?
No. No. For arbitrary n, there exists A and D. So the A and D depend on n. I think that's easy to destroy. If you just think of 2 colors, I think even with 2 colors you can, no matter, there are only countably many A's and D's, right? And no matter which A you picked, and no matter which D you picked, you have arbitrary time to sort of kill a progression of length n. Or to kill the infinite progression, you have infinite amount of time to kill it. So you just kill it them one by one and construct more and more of your coloring to know that this, in general, the A and the D will depend on the n. Yeah. So it's arbitrarily long, finite arithmetic progressions, but it's not an infinitely long, not one infinitely long progression. Yeah, thank you. That's an important distinction. And here's the dynamical theorem, which can be used to prove that. There are other proofs, combinatorial proofs of that theorem as well. But yeah, we're doing dynamics, so we're interested in dynamical statements. And this is a multiple recurrence theorem. Yeah. Let X be a compact metric space. and let T1 up to dd from x to x be commuting homomorphisms. Right, so you know what I mean, right? T1, T2 is equal to T2, T1, and for all the other pairs as well. So it's multiple recurrence. So actually, one strengthening of what we did before is that before we said, okay, for every homeomorphism, we have a recurrent point. We have a point that will return to itself. The first strengthening of that in this case, under this assumption that we have commuting homomorphisms, is that we actually find one point that is recurrent for all of them. But even more we are claiming. So let me give you the statement. Then there exists some x0 in X, which is multiple simultaneous recurrent, multiple simultaneous recurrent, and some nk going to infinity as k goes to infinity, so that t to the nk of x0 converges to x0. You should complain, what do I mean, t to the nk? Which t do I mean? I mean all of them. So not only is it the same point that is recurrent for all the maps, but it's also the same time. Okay, so that's the theorem. I changed my mind somehow. The D here is the capital N here, later when we prove it. But this D will be appearing sort of a ton throughout the proof, and often in the index or in the exponent, and capital N doesn't look so nice in the index and the exponent. So I'll keep N, the D here, and even though it's equal to the N here, never mind. And of course the D here is the difference, and the difference will be related to the N's here, never mind. But yeah, it's just looked too ugly to have capital N all the time in the index, and sometimes in the double index, and then it was a capital N. It's just, no, I couldn't do that. Okay, that theorem ain't easy. So everything else we did before was kind of easy. You had to have the right idea. If someone gives you the statements and you think it long and hard, you can come up with the proofs somehow. I wouldn't be able to come up with that proof by myself in a short period of time. So that theorem ain't easy. Yes?
What does the multiple mean?
Multiple means that I have D maps, and it's multiple recurrent somehow. And the simultaneous, with the simultaneous, I wanted to emphasize that it's the same time also. I also don't know how to prove this theorem in this formulation in 3 weeks earlier, in an easier way. If you cross out the simultaneous, it would be super easy within 3 weeks inside ergodic theory. So the multiple recurrent would be easy to prove using ergodic theory. The multiple simultaneous, I'm not sure. I don't see an easy argument for that, for the simultaneous. So that's an argument why it doesn't matter. There's no reason to wait for ergodic theory to help us, because it doesn't really help us. If we are aiming for the simultaneous, and the simultaneous is important for the application. It ain't easy, but it's fun. So maybe I should also emphasize something else. I said commuting, and I explained it, what I mean by commuting. If you don't assume commuting, it's nonsense. It's definitely wrong. The easiest example I could come up with is north-south is one map, and east-west is the other map. What do I mean? I take the circle. My first map, T1, is having two fixed points and is moving everything north, except the South Pole. And my second map is working on the same space and is moving everything west, say, T2. Then T1 has a recurrent point. It actually has two recurrent points, the North Pole and the South Pole. Those are the only recurrent points for the first map. The second map has recurrent points, namely the westmost and the eastmost points. They are fixed points and they are recurrent. But those are the only recurrent points for that map / for that map. There's no common recurrent point. Right? But they're also not commuting, so it's not really an example of the theorem. It's just testing why certain assumptions are there. The commuting seems to be really essential for the conclusion. Or maybe it can be, maybe it could be weakened in some sense, and I think people have weakened it, but you can't get rid of it. You might be able to weaken it, but you can't get rid of it. These two things generated a free group pretty surely, so they have satisfied no weakening whatsoever of commuting, but yeah. Okay, there are a couple of ideas that we'll have to use to prove that theorem. The first one is easy. We induct on the number of maps. So we'll use induction on the number D. To prove the theorem, we use induction on D. The case D equals 1, we already know. This was the earlier corollary. Yeah. The corollary precisely said there exists a point that is recurrent, and you just have to choose it from within a minimal subset. That was the proof of the corollary. Yeah, and we now assume that the theorem already is known for D, and we want to know for D minus 1, and want to prove it for D. We assume that, I actually want to assume two things, so let me say. One, the theorem already holds for D minus 1. And I want to assume something else, that X is minimal considering all D maps. I write it down and then I say why we can do that. That X is minimal in the sense that Y contained in X closed, Y equals T1, Y equals TDY implies Y is nothing or Y is everything. Why can I assume that? because I'm cheating, I just say, we look at the previous theorem that said that minimal subsets exist, and look at the proof, think about it a bit, and say, we could have used decommuting maps throughout the proof, and then the theorem would have shown that there always exists a minimal subsystem when you consider all D maps. So it's a different notion of minimal. Maybe I should say it's D-minimal. Maybe I say D-minimal, because it's minimal for the joint consideration of these decommuting maps. And yeah, I'll just write it down. We repeat the proof from earlier and restrict to such a system. Parentheses, we repeat the proof of the earlier theorem and restrict to a minimal subset, to a D-minimal subset. Okay, so those are two assumptions that we want to make. The one is without loss of generality, and the other one is the usual inductive hypothesis. Yes?
The only thing we would change in the proof from before was that in the lemma of Thom we would replace y is equal to ty with this condition.
Yeah. Yeah, we had this definition of the curly E, and in the curly E you just make the D invariance assumption. So this you would have to put in the definition of E, and that's the only thing that will change. Yes?
Do we need for that they are commuting?
Probably not. But you'll see the commuting many times, in particular when I start using the inductive assumption, we'll see how it will be important. I agree. For the minimal thing, you could just have a general group action and the proof would not change. Yeah. Doesn't have to be commuting maps. Okay, we need some notation. And somehow, the way I set up the notation, you'll see that there will be some steps in the proof because we'll really use some notation. Maybe I should say at some point that this connection that I'm trying to sell, this connection between dynamics and ergodic theory and Ramsey-type theorems inside combinatorics, was something that Fürstenberg found in the 1960s. And it has become a very active and beautiful subject in its own, with lots of papers every year on refinement and refinements of various directions of that connection. And the way we will prove the van der Waalen theorem using this recurrence theorem is sort of an instance of the Fürstenberg correspondence, named after him because he found this connection. So that will be much easier than proving the topological statement that we are aiming for. Right. Some notation. So we'll definitely have to work with the default product of our metric space with itself. We'll use the maximum metric if someone asks. And that just gives you the product topology. Everything is sort of natural. A sequence of tuples converges if and only if coordinate-wise we have convergence, the standard thing. No, nothing to worry about here. We will also use T1 cross TD as a map from XD to XD, which applies the first map on the first coordinate, the second map on the second coordinate, and so on. We'll also use the map that applies the first map in the first coordinate, the first map in the second coordinate, and so on, which is just T1 cross T1 from x to the d to x to the d, and of course the same with all the other TD hat is TD cross TD from x to the d to x to the d, and I promised you that the d will be in the exponent and in the index, and yeah, we already established that. And this commute, right? All of them commute. The S commutes with the heads, and they are all on the same space, so that's great. For n, which is a tuple, which is n1 up to nd, it's a d-tuple of integers. We define t to the n with underlined as the shorthand for t1 to the n1, t2 to the n2, and so on, td to the nd. Composed td to the nd. And now we would have the capital N in the index of a superscript, and no. Can only be done with small letters. And, well, if we can do this without the hat, we also can do this with the hat. I apologize, but these maps might be used, and we have the notation for it. So the hat, this is a map from x to x, and this is a map from xd to xd, which applies this map in every coordinate. Right? That's the relationship between the two. This is just the simple composition of my original maps corresponding to that n-tuple, and when I apply this and the same map in all coordinates, I put a hat on top. Some notation to get used to. Not everything will appear immediately, but there's another notation. For a little x, I write delta x for the element on the diagonal corresponding to the element x. And the last one, and then I have time for the question. I write delta subscript capital X for all the elements on the diagonal. So this little delta x for x in x. Full diagonal. I mean, I can't really draw the super high dimensional case, but I'm thinking of just that picture when I think of capital delta x. And this is just a point on it, right? This is a point on it, and this is the whole set. Some silly comments. This set is invariant under these maps. Because here I'm applying the same map in every coordinate. And if I start with a point where every coordinate is the same and apply the same map in every coordinate, then I get the same point in every coordinate. So to play with these notations, we have t hat superscript n of delta little x is actually equal to delta of t to the n x. Yeah, bit for x in x and n in CD. Presumably, this diagonal is not invariant under S, right? S is applying different maps in different coordinates. If I start with a point on the diagonal and I apply different maps in different coordinates, I probably don't end up with a point on the diagonal. If I do end up with a point on the diagonal all the time, then it's not so interesting because all the maps are the same map. And then the theorem is already known because you really just study one map. And simultaneous and multiple is kind of meaningless because it's really just one map. So I will have to think about the case where the S does not leave the diagonal invariant. The diagonal is not invariant, but it's invariant under these T hat maps, tautologically, sort of like that, but not under S. Good. Claim 1 of a couple of claims to come. So there will be 1, 2, 3, 4, I think 5 claims, and 1 lemma in between. But yeah, just so that we have some overview of what's going to happen. Minor overview. And the first few games are kind of easy. They are playing with these assumptions, with omega limits. And then we get to a point where, in some sense, some classical analysis becomes important. But you may not have seen it, so we'll just talk about it all the way. Claim A. I'll take the full diagonal, and I look at the omega limit of the full diagonal under the map S. And I'm claiming this is not empty. I'll write down what it means sort of in less concise notation also. But yeah, let's do that. In words, there exists x0 in X, which is this guy, and a sequence. Sequences we have, right? Also in the theorem, we're interested in the sequence nk. So that looks nice like in the theorem. Sequence nk going to infinity so that and yk in X so that T1 to the N1 yk converges to x0 and Td to the Nd to the Nk, Nk, T1 to the Nk, Td to the Nk, yk also converges to x0 as k goes to infinity. That's what it means if you unfold the definition of the omega limit set of a set that I gave you before. But it's kind of a funky notion, right? Because we have a subset, and it is invariant under some maps, but just not under the map that we're considering. We are taking the S map. The S map is the product where we apply the different maps in different coordinates. And we claim that we can find a point in the diagonal that can be approached simultaneously from points on the diagonal using the different maps in different coordinates. Right? So this here is equivalent in, again, bookkeeping, to S to the Nk delta of y applying to delta of x, converging to delta of x as k goes to infinity. Right? This statement, the product topology, is precisely these statements. And this is not a delta. On the left-hand side, we don't have a delta because the S uses different maps in different coordinates. Never mind. For the proof of claim A, we use the inductive hypothesis. like so. We define new maps, R1, and up to RT minus 1. And somehow I want to hide the last map. Yes? X0, yes, thank you. I didn't bring the chocolate, sorry. So I want to hide the last map, but I don't want to completely forget the last map. Yes?
Can also be a YK.
Yes, a YK, yes. Now it becomes embarrassing. I really should have brought the chocolate. I want to hide the last map, but not completely forget it. So I take R1 is T1, TD inverse. RD minus 1 is TD minus 1, TD inverse. So I use the inverse of the last map in all of the maps. By assumption, and these are all maps from X to X, they're all homomorphisms and they commute. Just as before, they commute. By the inductive assumption, there exists X0 in X such that and nk going to infinity such that Rj to the nk of x0 converges to x0 as k goes to infinity for j equals 1 up to d minus 1. Okay. In the game, I had created a bit more flexibility. I'm not saying that my point is recurrent, my x0 is not recurrent. And created the possibility that the other point on the diagonal is a yk depending on k. And this is now how I define my yk. We define yk equals t d to the minus nk of x0 at some point in x. That depends on k. Then no, without the minus, sorry. Without the minus. With the minus, without the minus. Okay. Sorry. With the minus. With the minus. Yes, with the minus. Sorry. So I look at T j to the nk of yk and claim that this converges to x0 as k goes to infinity and j is something between 1 and d. That's a bit confusing, but we'll think about it. Somehow the case j up 1 up to d minus 1 is different than the case j equals d. So let's look at the last case first. When j is equal to d, I'd have td to the nk of yk, but that's td to the nk minus nk of x0, that's also called x0. And then x0 converges to x0. So that's true. So that's this case. And in the other cases, it's again just bookkeeping, because here, the inverse of td to the minus nk is hidden, right? The inverse of it is sort of built into the definition of R. because the maps commute. I think if we didn't see it before, we definitely see it here that we are using that TD commutes with the other maps. So this statement is actually equivalent to that statement for J less than D. So we get all cases. But that statement is precisely the statement that I claimed, claim A. There exists a point on the diagonal that can be approached under the map S from a sequence of points in the diagonal. That's what we have proven. And for this, we only needed the inductive assumption somehow. Yeah, I'm running out of time. Let me state the next claim. Not write down anything, but let's see why we believe the next claim. And that would already be the beginning of tomorrow's lesson. Claim B. Delta x is contained in the omega limit of delta x. Up there I say it's non-empty. Now I say no, it's not non-empty. Everything, the whole diagonal is in the omega limit set. Why could that be true? That's a bit of a stretch. It's not completely obvious because there's quite a few things floating around. So because there's so many things floating around, it's not totally clear which one of the things could be relevant here. I'm claiming that the head maps are important and the minimality assumption is important. So I'm claiming this can be used, can be proved by saying, first of all, that this omega limit set is invariant under the head maps. Again, because S commutes with the head maps, and because the diagonal is invariant under the head maps. Because the diagonal is invariant under the head maps, the omega limit, and the S commutes with the head maps, the omega limit set will be invariant under the head maps. Which means that the intersection of this with that will be invariant under the head maps. But the intersection will be a closed subset of this set. And X is minimal and the diagonal is isomorphic to X. So we get a closed subset of a minimal system that is not empty because of the first claim. So it must be everything because of the minimality. That's the proof of the second claim, which we'll write down tomorrow. Thank you.